Great. So thanks again, and I would like to thank ADIA for the invitation. It's great to be back in Abu Dhabi. I'm saying to be back because I have few familiar faces here in the room. I worked with a number of people here. I spent a few years in Abu Dhabi working with at Masdar Institute as a professor before I moved back to the States. So I try to couple the knowledge I have of the region and the weather and also the know-how that I learned in the States for using models and data, etc., from different sources. So I'm going to talk about the use of AIs, but also I'm going to compare it to the models that we are using also and show their limitations and why we need really to transition or at least consider AI-driven model. So I'm at Stevens, as I've mentioned, and Stevens is located in New York City area. So New York City metropolitan area. We are right in Hoboken on the Hudson River. We have a very nice view on Manhattan skyline. Most of the time it's nice to be there, but when we get one of those major events, it gets really messy. So in 2012 and many other events, but the 2012 one, we had Hurricane Sandy, which is one of the major events that hit the area. And that's not an AI-generated photo there, it's a real one. So New York City subway got flooded and it was really messy. And we are talking about Wall Street, we are talking about the United Nations there, we are talking about billions and billions of dollars at stake in that area. So we better have the weather forecast right. And we better also predict the when and where exactly and what's the magnitude of those events. So Sandy, for instance, caused about $19 billion. And why Sandy was critical and specific? Because it was about 14 feet of a surge from the ocean. As you know, Manhattan and New York is coastal, so we got a lot of water surging from the ocean, but we also got a lot of rain inland. So what happened is that water from land is trying to go to ocean, and ocean water level is already high. So you have like a compounded effect of those two components. Water coming from deeper inland, rushing out to the ocean, but the ocean says, I mean, the water level is already high. So that's why it got really messy, and that's what we call a compounded effect or a compounded event. And we are seeing more and more of those compounded events where ocean surge happen simultaneously with heavy rainfall. So what to do? We have to perform, we have to run sophisticated models and then improve them, and also consider their limitation and then address them. The bad news is that those events, those extreme events, are not getting any better in a way that they are getting more and more frequent. And the Northeast, based on the climate report, the recent one that came out, is showing a 55% increase of extreme events, the 95th percentile of extreme event. It means that the number of extreme events in the Northeast of the US will keep increasing, unlike Luca's western side, for instance, of the ocean, of the state. So we have to expect to see more and more of those Sandy-like events with all the damage that that should come with it. And noting that about 40% of the population lives in areas that are coastal, so we have always that risk of getting the ocean and the rain from runoff basically compounded together. To understand this compounding effect, we have to run an ocean model and a hydrologic model. So the ocean model will run on the ocean side, of course, but most of it will mostly consist of hydrodynamic circulation plus wind stress. And the wind stress will move water at the surface and create the wave. On the other hand, and on the other side of the shoreline, inland, you have hydrological models that are driven, as Yusuf mentioned, mostly with precipitation. So on the other side of the shoreline, deeper inland, we have to get the precipitation right. And that's the dilemma. We have to have the weather right and the circulation right on the ocean, so we can get the surge, elevation, and timing, okay? And the timing of the surge is very, very important, because when you have a surge coming from the ocean, you have to know exactly when it's going to happen to compare it to the tide. By chance, when Sandy happened, it coincided with the high tide. Had that it came a bit early or a bit late and it coincided with low tide, then we could have saved many, many billions of dollars of damages. So knowing the timing of the surge from the ocean is very important. And that's why weather is very important in that perspective. On the other side, the precipitation is also important. It's timing and magnitude because it will define how much water we're going to get from deeper inland and when we're going to get it to compounded with the ocean side. Now, as Yusuf mentioned, I mean, we have a wealth of information to tap on. We have a lot of satellites. NASA, NOAA put a lot of satellites in addition to ESA, the European, the Chinese, UAE also, they are starting missions here. So we have really an abundance of data, and unlike in-situ data or ground-based data, satellite data, most of the satellite data are in the public domain. So most of those satellites were paid for by government, put on a rocket ship, put in space, collecting data, download the data, and then disseminate the data online. So you can build a career just looking at those satellite data, intercompare them, and leverage them to improve your model and predictions. Again, most of the data are free, unless they are quite high resolution, the hyper resolution data. In the meter or sub-meter resolution, those you have to pay for. And there are programs, if you are a university, et cetera, to actually get them for free from some providers, like Planet, for instance. Now, the problem, we can tap on the amount of data. The problem is that the abundance of data doesn't necessarily mean that we are making progress. And I underscore the word necessarily, because as a matter of fact, I mean, when we collect all those data from different agencies, if we look at this graph here, this is the 100% bar, where that represents the total data that we get from satellites. Those data we collect are about clouds, their location, water vapor, temperature in the atmosphere, soil moisture, all those data. The data we collect are supposed to be integrated in the model. So the model, as the model is moving in time step by time step, as soon as we receive data, we tell the model, hey, guide yourself along the data I'm feeding you. And that's what we call data assimilation, right? So the model will be zigzagging around those data, minimizing the bias between the prediction and what we are feeding the model with in terms of data. But the problem is that when we look at the amount of data that's being assimilated, it drops down to almost 2%. From 100% here, we select about 7% or so of the data, and then we only use 2% of the total data to guide the model through. And then the rest will be thrown away, basically, because of quality reason, because of the timing, or simply because of resolution that is not appropriate for a model that what we run. And that's a problem. So that's one of the conclusions we could draw here is that an abundance of data doesn't mean that the models are getting better. The physics-driven model, because those data are being, I should highlight that, those data are being assimilated in physics-driven model. We are not talking about machine learning models. I take the example of precipitation. So this is a rainy cloud, like any rain you could see. And this is how we could observe a rain. We could put rain gauges, basically bucket in your backyard or outside to measure how much rainfall you got in terms of total. You can also have ground-based radar, like those you see at airports spinning, looking at the same rainy cloud. Then from space, you can have a satellite or multiple satellites looking at the same rainy cloud. You may have more than one ground-based radars and more than one rain gauge. And we are talking about the same event. Even though we are talking about the same event, those instruments measuring and observing the same event would be reporting different values. Which one is right, which one is wrong? They are all right and they are all wrong, because it depends on how you define a truth. We don't have a benchmark here. They are all measuring, they are all observing, looking at the same thing, but looking at it from different angles. So the satellite will only look at the top of the cloud, not necessarily what's going on in the bottom. The radar will look at this side, the other radar will look at the other side from different distance. So they arrive at different levels of the cloud, and that's why they report different values. So even if you collect more data, if you feed this instrument-based data into the model, then you may actually create a bias in the model if the data is not coherent. And that's one of the issues that we face in the physics-based model. Even if we collect data, we invest in platforms to observe more and more. Collecting more data doesn't mean that we are better informed. That's the moral of the story here. If we collect more than what we need in terms of data, especially if the data is not coherent, we may mislead the physics-based models, and we may create an inherent bias in those models because of what we are assimilating. Okay, so now at Stevens, dealing always with physics-based models, we generated what we call Stevens Flood Advisory System, looking at New York City area. New York City is where that high concentration of stations is. It's a regional model, and then cascading nested models at different resolutions. And then this is the model I referred to earlier that accounts for the compounded effect. It looks at the hydrodynamic, coastal processes, and the land part, driven with an atmospheric model. So we are basically closing the loop: atmosphere, coast, and then land processes. The model has been used for more than 10 years by different stakeholders in the region, paying for its maintenance and development, like the Port Authority of New York and New Jersey, many other agencies and users. Now, the model was successfully used for the prediction of many events, more recently like Sandy, but we have Irene and many other events. We look at this level of flooding, which airport or which train station will be flooded, and what would be the level. That's why MTA, for instance, with about 30 million people moving in that area, metropolitan area, they really need that type of information so they can act and close train stations, subway stations, etc., on time, and manipulate resources, buses, etc., to evacuate people. The model, as I said, on the coastal area is a cascade of different models with different resolutions. The highest resolution, as we get to New York City area, is in the meter scale. So we move from 4 kilometers cascading all the way down, nesting models and meshes to the meter and the sub-meter resolution. On the inland side of things, we use open source models. On the coastal side, we use our university-built model. So we have different atmospheric forcing. We don't. So here's the thing: when you run a model, you use an atmospheric forcing. But as Yusuf mentioned, you have many people telling you how much rain you'll get, and many agencies. You have the NOAA, you have the European, you have the Chinese model. So which model you will use? What we do is that we include all of them. The US one, GFS, the European, the Canadian. We create about 100 weather forcing. So you may ask me, but this is even more confusing. Why? I mean, the data is already an issue, so why you include more data when it comes to weather forcing? Well, we do it because, again, we don't know what the truth is. We don't know which model, which weather data is the reliable one. So what we do, dump them all in and then use them to run the model. The model will give us as many prediction as the weather forcing we are using. So if we use 100 what we call members or different weather forcing, we will get 100 forecast, 100 prediction. If 50 of those predictions will tell me Manhattan Battery Park will be flooded, then the likelihood is about 50% for that Battery Park location to get flooded. And that's how we calculate the probability, basically. So we use more members or more weather data to be able to create probabilistic prediction rather than being deterministic in our prediction. And that has been very helpful. So we were able to use that in a probabilistic way to get different percentiles, the 50th percentile, and the extreme case, the 95th percentile. So we ran all those weather models, and then we have like probability distribution. We use the different extremes, the two tails, the best scenario, the worst scenario, and the middle. And that's what we report, basically. Because these are the representative cases, the two extremes and the middle, that we use to save on the computational cost, basically. We also, similarly, we exploit deeper inland, more high-resolution data, like in this case with a model called WRF Hydro, that is an open source. in this work here, we used citizen science information, like this one here, to validate the model. We didn't have any observation, so we used data. We know what's the size of the tire of the track. We know that's the elevation, so we pretty much estimate the water level at that location, and we compare it to the model output. Similarly here, what we did here is that we started to, so those images were from social media, and if you get an image from social media, from Twitter, let's say, most of the users, they don't geotag the picture, so, or Facebook, unless you are a Facebook employee. You can get access to the data. But if you are a Twitter user or a or Facebook user, when you look at the picture, you don't have the metadata of the picture. You only get the picture, right? You can download the picture, but not the metadata. The metadata include the location. Okay, Twitter, one of our X now, they communicate some of the metadata in a way that they don't give you the precise location, they give you a radius, an area where the picture is likely to be taken. And what we did here is that we geotagged the images with landmarks in the area. We know radius, and then we search for landmarks, and then we geotag the location automatically. Now, the lesson learned from these models is that we have challenge one, which is when we run different ensemble members, 100 of them, we have to do it for the coast and for the land part, and we have to do it for more than 100 times for 7 days ahead. It really requires a good computer. So that's, and then sometimes you have to do it on an hourly time step because the timing, as we said, is very important. So that gets very challenging. We are talking only about New York area. I'm not talking about the globally and digital twin. That's another challenge, another story. So only for New York area, it gets really messy. Challenge two is what our friend Yusuf mentioned here, is the complexity of the processes. I mean, just to understand the figure is challenging, let alone modeling it and then make sure that the model is capturing exactly what's going on in reality. So the capturing exactly the physics and as the way they interact, exactly the way they interact is challenging. So that's a challenge too that also it's a handicap for the physics-based model, especially when we have the loop of the coastal, the atmosphere, and the land all together mixed in the same model. Now, challenge three is the resolution, because our stakeholders and users, they want to know when the storm will happen, the timing, the magnitude, and the location. When it comes to location, you cannot tell someone, you know, it's New York City area, we know roughly when it's going to hit, but it may hit in New Jersey and not New York. I mean, what kind of information is this? It's not really useful to evacuate people based on a very rough geolocation. So the high resolution is very important. And that's a challenge, because when you do everything, and then the client asks you for a meter level resolution to get a level of street flooding, then it gets very challenging. And that's challenge number three. This model here, it's running flooding, but we noticed actually the users, they don't only need the water level, even it's true for Dubai here and Abu Dhabi, there is flooding. Water level is what we usually hydrologists communicate. So there is flood inundation, you communicate how many feet of water or meters here you're going to have at that location. But during flooding, what is more risky and more critical is the velocity of the water. If you take the same flood inundation level, like a meter, whether the water is standing or the water is flowing at the same elevation, there is a big difference. The one flowing at the same elevation of 1 meter would have more energy, more momentum. It will be more critical. So that's why we communicate flood inundation in terms of elevation, but also the velocity. It makes a difference between carrying a car away or leaving it at its place, or a pedestrian to be drowned or not. So the velocity, it becomes very important. Now, we made the shift. We understood, like many others, that machine learning and AI-based models, they have this advantage of emulating the same function that relates the input to the outputs in a physics-based models. So they emulated, research starts back in the 80s in NOAA, to emulate the physics-based model in a way or another relating the input to the outputs. And then, you know the rest of the story and how it evolved. So we started to mimic those approaches. First, we started to look at the US scale in this study that was published a year ago. So we used the LSTM model to predict stream flow. This is more of pluvial flooding across the states. We were able to do that in a reasonable way based on what we call the KGE, the performance metrics for stream flow. The problem we face here is that most of the rivers in the US are regulated. Regulated means they have dams, and those dams are controlled by operators. So there is someone sitting there, he has control on a gate, a spillway on a dam, of a dam. So they look at the weather forecast. Look, I will talk about it in more details later. And then they decide to open or close the dam. And then as a hydrologist, if you model this, if you don't have that action in your model, then your stream flow downstream will be off. So the solution is there are two options. It's whether to call every single operator of a dam and ask him or her, how do they operate the dam? What's the practice? And then try to code that in a model. And good luck if you want to do that. It's almost impossible. And the alternative was to use machine learning to see what was the history of operating that dam in the past based on how much of inflow and how much of releases. So machine learning was able to infer in a more or less the operator's rules. In a way, they captured how the operator reacts to storms, when do they release preventively to avoid flooding. And we coupled this with the previous model to improve stream flow forecast. Then we looked at precipitation. We looked at high-resolution precipitation from MRMS and other high-resolution data at 1 kilometer to 2-minute interval in the US. Then we started to, this is supposed to be a video. I don't know if it works or not. But this is supposed to be a video that should play. So we looked at these events. No. If you click on it, maybe it will play. I don't know. Otherwise, imagine. Yeah. No? Okay, that's fine. So this is New York City area. What we did is that we take the high-resolution precipitation, and then we moved in time to now cast the effect of precipitation. And then we zoom in at the station, and then our model will tell us how much rainfall we'll have in the next hour or so, or two, and then the location for each station, and then the return period. So this is used by our stakeholder extensively. So this now casting process takes the observation from the radar and the map of the rainfall, and then move it in time. That movement would assume it's not a simple shift in space according to the wind, because as the cloud or the rain moves, it would grow or decay. Okay, so so the process mimic that dynamic, and then it copies more or less the morphing AI-based techniques. And this is an example in one of the applications that Noah published. It morphs, so you have a time step, another time step, and this hurricane is moving in between. We would like to know what would happen in between. So the same way we morph faces, which is a very common AI application, we started to morph storms in between two time steps. So usually the global models, they update every 6 hours, but 6 hours is too long for an extreme event, for a weather disaster. You would like to know what is going to happen in between, within the 6 hours. So we morph the movement. So we tell the weather model, this is the initial condition, this is the last condition. Try to see how you're gonna get there. So the morphing is one of the applications that we are interested in. And then we used advanced techniques for segmentation of satellite data that we do for NOAA, and NOAA is using our data. Now we started to run forecast model and AI-based weather models as well. Forecast is, as Yusuf mentioned, is NVIDIA weather model. It's here. We also run our regional weather forecast WRF over New York City area, and we use GFS. ForecastNet is about 25 kilometer resolution. Our regional model is much higher resolution, 1 kilometer resolution over New York City area. So now what we are, and GFS is about ForecastNet resolution. So what we are trying to do now is how we can bring this to this. I mean, we understand that this is really simple model. I mean, if I mean, the script you can download it easily, and the script to run it are quite straightforward. When I worked with my PhD students on that, I was really amazed. I mean, you can run a global model like this one in nothing. On a workstation, you don't really need an HPC to do it. On your laptop, you can run ForecastNet. It's not really rocket science. So I'll encourage you to look at that. This requires an HPC and a good model to a good workstation or a computer to run. But this, because of the resolution, but this really not. It's coarse resolution and you can do it. But now how I can leverage this to bring it here? That's what we are working on right now. Hopefully next time I can share with you the updates. We are preparing the paper. But we started to look at the outputs, and we found that our physics-based model, which is more costly, luckily is giving us better results compared to the in-situ observation from the rain stations in New York City area. We looked also at physics-based models to run about tropical cyclones, 10,000 of them or more around New York City area. So we generated a rich archive of data, and then we used them to couple the hydrodynamic model I showed you earlier with this high-resolution mesh using two models called ADCIRC and SWAN. And then we looked at how those models will be generating surges and coastal flooding in New York City area. This is with AI. So the models, the rich archive of the possible storms that could hit the New York City area allowed us to build that archive of data to train in the AI model. We are doing the same thing with the weather model, mimicking NVIDIA's CoreDiff. Or probably NVIDIA are copying us. I don't know who's copying the other. But yeah, it's the same mindset. Now, lastly, we also invested in developing observations more at a high resolution. AI cannot, in a way, create something that is, I mean, in a generative context, it could create information. But the weather models, they cannot downscale without guiding them. They just don't. So what we did is that we started to invest in a network of flood sensors in New York and New Jersey area. And those flood sensors would give us information about flooding as it happens in real time. And we are doing, for each sensor, we have a flood sensor here and a rain gauge, very low cost. The sensor rain and flood together, with a solar panel, a data logger, and an antenna, everything, they cost about $300. It's really affordable, and they are connected peer-to-peer. So we don't really need a cell phone to get the data. So they can connect to a low radio frequency, basically LoRaN-like network, and then they can stream the data in real time. Very cheap, very convenient, and a very good school project for whoever is interested in the room here. We work with USGS in the same perspective to analyze data from ground stations. There are hundreds of them, about 1,000 in the US. We classify the data for them. We do weather degradation because they throw a lot of data away because of the weather data they have. So we do dehazing, removal of rain, glare, etc., so they can analyze the data correctly. How am I doing in time? I'm fine. Okay, perfect, excellent. So we are dehazing the data, correcting the data for them, and then they use the data, the corrected data, to augment their potential to look at flow conditions in the US. We also give them like a dashboard of a health check across the US. We tell them which camera is doing a good job, which camera is actually being impacted by weather, and what type of weather degradation. With the classifiers we have, we are able to identify what type of weather degradation the camera is impacted with, and what time of the day as well. So the users, the stakeholders mostly, they can develop some understanding of their data. Lastly, optically, without connecting in any way with the rivers here, we can, from the cameras with AI, we can, and computer vision techniques, we can measure from cross-correlation of frames, we can measure velocity, surface velocity, and then infer the bathymetry of the river and determine the flow. So this is really a step forward in the application of computer vision in our area, in our field. in a way that optically, again, you determine the distribution, the surface velocity. You can determine the average velocity and then multiply this by the depth, knowing the bathymetry to get the flow optically without any investment in gauges or any other thing. Last thing, we looked at social media. This is a hurricane Ida moving from the Gulf to New York City. We looked at tweets, and we looked at sentiment analysis with models. And then you can see throughout the days when we started to predict the event, there is a peak. We started to have a peak, with tweets related with the name of the hurricane. Then the peak happened when the hurricane hit. Then the tweets are phasing out because people start to forget about the hurricane, but the sentiment persisted in a negative or positive way. Same thing for the classification of the sentiment. When the hurricane hit, actually, when the first landfall happened, we have a balanced sentiment between positive, people happy and sad, but then we have a dip in the negative side of the things, and we were able to do that also hourly. So with X or Twitter or Facebook, you can fetch those tweets in real time and analyze that with the sentiment analysis model in real time as well. This is also very informative for crowd management, many other applications, the use of social media. So for the sake of time, I'll probably very quickly say that big data is around and it is quite transformative in our field. In my lab, I'm in the civil engineering department. I have more students, PhD students, with a background in computer science and electrical engineering than civil engineer. And that tells a lot. I'll leave you with a nice picture of our campus. That's New York, and this is our campus. That's our students' dorms, by the way. That's the best view in the world for students' dorms. Thank you so much.
Thank you, Dr. Temimi, for that insightful presentation. We'll take just one question. It's okay. Professor Porco.
Thank you, Marouane, and thank you, Youssef, for the very nice presentation. So I have a comment rather than a question that is more related to wrapping up after the session of this morning and the current session of this afternoon. So we started talking about sustainability in AI, and we got a very insightful presentation by Stephen Chu with some alarming messages. Then the subsequent talks, what I see is unsustainability in AI, because I see some kind of obsession for getting more and more data on the basis of AI models. I'm not sure this is the right way to go, and if we want to pursue accuracy. Not the right way to go because it is not sustainable, and also conceptually, I'm not sure this is the right way to go because these models are actually depicting variability for a trend, but not trend for a variability. I would like to see more balance between deterministic and stochastic approaches to pursue some balance within sustainability of the AI systems.
Yeah, that's a problem, I can tell you. We have a lot of misbalance in the data we use for the training of the models in a way, because those extreme events that we are mostly interested in are rare. So they are not that representative in the data pool we use to train the model. And by design, the models are trained to mimic the behavior of most of the representative data that they are fed with. There are techniques to create better balance in the data with data augmentation, basically, but they come with their issues. Still, we are gaining a lot with respect to the physics-based models, I think. Maybe hybrid approach in WRF, for instance, which is a physics-based model that Youssef showed with that complex diagram, we started to emulate parts of the model, not all of it. So you come probably to the radiation scheme, which is a physics-based in the bigger machine. You cut it out, and you're placed with an emulator that is data-driven. But the machine itself would be better informed and would be able to capture those outliers in a better way. Right? Probably the hybrid approach is more viable here.